Today's lesson is a continuation of section 5.4, write linear equations in standard form. Again, last lesson we started talking about what does standard form look like compared to what we've been doing. Here's standard form, ax plus by equals c. We've been making equations or writing equations in slope-intercept form, y equals mx plus b. The biggest thing I want students to realize, or the biggest difference I want them to realize between these two types of equations, is that x and y in standard form, x and y, those two terms are on the same side of the equation, whereas in slope-intercept form, y is all by itself on one side. So what we're doing is now writing equations in standard form. Well, as we talked about last lesson, there isn't always a great way to do that, but today I'm going to talk about one nice way that one nice use for standard form, and it's when certain types of word problems set up well with this form of equation. So we will see there is a nice way to just make an equation in standard form as opposed to having to just kind of manipulate like we did last lesson. First thing I'm going to talk about though is a couple special cases that fit into this section. Horizontal and vertical lines, making an equation, making equations of these types of lines. And again, they are kind of special case, but something we still should know about. Again, if there's something to write down on this page, these lines right here are in red. So definitely if you're taking notes along with me here for this lesson, jot down that horizontal line is a line that goes from left to right. Again, the straight across line. And a vertical line is up and down. And if you're looking at them on the graph that I have down here, the vertical line is the red one here. And again, horizontal line from left to right, this is the green one. Some problems today are going to ask you to write equations of lines that are horizontal and vertical. And what they'll do is they'll give you a point on the grid, like this problem I have down here. Write equations of the vertical and horizontal lines that pass through the point 4, 3. So here's the point 4, 3, as I've got marked on the grid. And I've got a vertical line through it, the red one, and I've got a horizontal line through it, which is the green one. So what we're going to want to do is there is an equation for each of those two lines. And we'll start off with the green one, the horizontal line. So I think this one will make a little bit more sense with what we've done here in the past in class, or with some other problems that we've written, or equations that we've written. If I look at that horizontal line, think about slope-intercept form. When I'm making an equation in slope-intercept form, I need m, the slope of the line, and I need b, the y-intercept of the line. Well, that straight across line, the horizontal line, there is a slope for that. That's the zero slope line that we've talked about in chapter 4 and even in a little bit in this chapter, but that's a line we have seen before. That has a slope of 0, so I can say m is 0 for this problem. What's the y-intercept? Well, again, here's this green line, and I'm looking where does this green line hit the y-axis, and there's a spot. It's right here, and it looks like it's at 3. And I think that makes sense because we're saying this is a horizontal line that's through the point 4, 3. So that means we've gone up 1, 2, 3 spots. From the x-axis, we've gone up 3 spots here, and then it's just straight across. So that makes sense that the y-intercept is also 3, since the line is just flat across everywhere. So if I'm picking out m and b, well, now I have my two numbers that I need. The slope, m, is 0. The y-intercept is 3. So if I was making this equation, it might look like y equals, well, 0x plus 3. But 0 times anything is just going to be 0, even a variable. So that part's just really going to cancel out. So this equation really ends up just being y equals 3, which was the y coordinate over here. And again, I think that makes sense if you kind of think about it. All the points along this line are going to have the same y coordinate, which is 3. Like if I go left 3, up 3, here's a point right here. This point is negative 3, 3 that's on the line. Okay. If I go a little farther back, this point right here is negative 9, 3. They're all going to have, every point on that line is going to have the y coordinate of 3 no matter what. So that's why the equation says the y coordinate's 3 always. Doesn't matter what x is. Doesn't have any effect on the equation. But y is always 3, so the equation is y equals 3. And again, I guess this is standard form because y is on one side. And if there was an x, we could put it over there too. And then it has our constant c on the other side. So I guess they kind of throw this in the standard form section, but it does count for standard form. Y equals 3. Well, knowing that horizontal line there is y equals 3, let's look at the vertical line. In this case, 4 is the x coordinate. And using kind of similar logic here, notice all the points along this red line are going to be 4 something. Like this will be 4 negative 2. Or down here it'll be 4 negative 7. Or up here it'll be 4 9. So if all the points are always 4 something, then this line always has x coordinates that are 4. In the horizontal line, all the y coordinates were 3. So the equation was y equals 3. On the red line, the x coordinate's always 4. So what do you know, this equation also just as short as the other one. It's just x equals 4. And again, I don't think we've ever written an equation for a line like that before. It's not slope-intercept form, and that's why I guess they call it standard, because they do have x on one side and a constant on the other. And if there was a y term, it could be on the other side too, but in this case, it kind of cancels out. So we just have x equals 4. So and as we've seen this line before too, it's a no-slope case. If you remember the line that's straight up and down, this is the no-slope case. So it doesn't really fit well with slope-intercept form because there's no number even associated for the slope. So that's why we couldn't make it when we had slope-intercept form. But now with standard form, we can make it. And again, it's kind of a special case, but just something to keep in mind. So going through maybe just one more example of one of these problems, because again, you'll see a few of these in the homework. They say write the equations of the horizontal and vertical lines that pass to the point negative 5, 2. So here's that point, negative 5, 2. Well, again, we will look at the horizontal line first. If I was making that one, I could say it has a slope of 0. But like I was talking about above with that previous problem, I think the easier way to think about it is just look at all the points that are along this horizontal line, this green line. This point would be 2, 2. This point would be 7, 2. This point back here would be negative 10, 2. They're all going to have a y coordinate of 2 every single time. And so what do you know? This is kind of a special equation, but the equation ends up being y equals 2. Because the y coordinate is always 2 along that line. Doesn't matter what x is. X doesn't affect anything, but the y coordinate's 2, so what do you know? The equation is y equals 2. Same thing's going to happen for the red line. Since this line goes through the negative 5, which is 5 to the left here, all the x coordinates are going to be negative 5 something. Negative 5, negative 1. Negative 5, negative 6. Negative 5, 8. Okay, every single point will have that first coordinate be negative 5. So what do you know? This equation is x. The x coordinates are all negative 5, so it's x equals negative 5. So again, kind of special cases about the horizontal and vertical lines, but something else that they do put into this section, so something we'll keep an eye on. So those first 3 problems were just kind of, again, some small things we'll run into once in a while, some kind of special cases, but really the section is also talking about standard form equations, and like I mentioned Friday, or like I mentioned, sorry, or whatever yesterday was, the previous lesson, there are nice ways we can make standard form equations if we have an equation in slope-intercept form. I can change it around and manipulate it to get x and y on the same side. So we can do that. But in this case, for standard form equations, there is a nicer way you can make them too, and there is a nice usage for standard form equation. It's what I have here in red. Some word problems set up very nice with standard form, some linear word problems, and they wouldn't set up so nice with slope-intercept form. So here's another good way that we can use standard form. Again, standard form looking like this, ax plus by equals c. But it's in word problems where we'll see something like this as I've described here in red. Again, if you're taking notes along with me, this is what you jot down. There'll be some word problems where there'll be 2 rates of change in the problem. When there was only 1 rate of change, we use that as our slope. And then usually we had like a y-intercept, like a b. And we put our equation in slope-intercept form. Well, in a problem where there's 2 rates of change and then some kind of ending total, this is a good equation that we'll set up in standard form. And again, we'll talk about maybe a few examples like what this might look like. So I've got here an example I've just kind of made up of a problem that will set up nicely with a standard form equation. And again, it's something that wouldn't set up even, it'd be a little tougher to set it up with slope-intercept, but it's a linear equation, but it'll set up nicer in this form. Problem says one baseball slash softball statistic is to count up the number of bases a player is hit for. This is called total bases. So we'll say Joe Joe has only hit for doubles and triples this year. So he hasn't got any singles or home runs at all, just doubles and triples. So far he has 18 total bases just by hitting doubles and triples. Part A says write an equation in standard form that models the number of possible combinations of doubles and triples that Joe could have hit for. So if a player gets a double, that's 2 bases. So then we say you've got two total bases so far. If they hit a triple, they've got 3 total bases. Just say in one game they hit a double, then they hit a triple. That'd be 2 plus 3. They'd have 5 total bases. So again, this is a statistic that you could keep for a game or for a season or for a week or whatever it may be. But we're going to make an equation that would model, let's say Joe has only hit doubles and triples. And he's got 18 total bases we know so far. What's a combination of doubles and triples he could have hit to get to 18? Well, again, an equation like this that has 2 kind of rates of change. Those are going to go in for A and B, and then usually some kind of total amount will be C. In this problem, we can kind of see the total number of bases we're talking about is 18. He needs to equal 18 bases total. How many doubles and triples he's hit? It's all got to equal up to 18. So that's like my total amount. That's going to go in for C. A double is worth 2 bases. So in this case, it's like 2x, and x stands for however many doubles we've hit so far. And then a triple is 3 bases. So that's like 3y. So here's a standard form equation again that models nice for this word problem. That would tell me I could model to figure out how many combinations of total, or how many doubles and triples in this case I could hit, or Joe could hit to get 18 total bases. Again, 2 stands for each double is 2 bases, so x stands for the number of doubles that Joe might have hit. 3 stands for how many bases you get for a triple, and so y is how many triples he may have hit so far. And so 2x plus 3y equals 18. Then part B says list 3 combinations that are possible. So for Joe hitting doubles and triples, he's got to get 18 total bases. He's only hits doubles or triples, so he either gets 2 bases every time. He gets 2 bases, he gets 3 bases, but he's got to make some combination of those to get to 18 exactly. When students are doing this can be a little bit of guess and check. You could try plugging in a certain number of triples and then seeing, well, how many doubles would I need to make that work also. So you can almost make some kind of table. Or you could, some students are kind of good at thinking these out too, and figuring out, okay, well, if I had 3 of these, and they kind of do it in their head, and they can figure out, oh, I need 5 of these then, or if you can do that, that's great. Okay. What I would say maybe as a good suggestion though, you could start with a table and say, okay, well, what if I just hit 0 doubles? Okay, just start with 0 and go from there. Well, if I hit no doubles, that'd be like putting in 0 for x. And so 0 times 2, well, that would just get rid of this. So all I left is 3y equals 18. Divide 18 by 3, I'd get y equals 6. So when I put in 0 for x, I got 6 for y. What does that mean? Well, that means if I hit no doubles, I would have had to hit 6 triples to get 18 bases. So that's a possible case that could work. Okay, you could hit 0 doubles and 6 triples. By also doing guess and check, you may come across combinations that won't work, because maybe you'll have half of something or 0.3 of something. So in this case, let's keep going here. What if I say that I hit 1 double, or Joe hits 1 double? Okay, if I put 1 in for x, then again, it's almost like a little equation I could solve. Well, 2 times 1 would be 2, and then subtracting 2 from both sides, I get 3y equals 16. Divide y by 16 by 3, I get 5 1/3. And so when we're doing these problems, we have to kind of think about, like, real world, like, does that make any sense? Could he hit 5 1/3 doubles? Well, no, he couldn't. So 5.3, you could put that out as a combination for a second here, but realize that wouldn't work. So I don't want students to put a combination like that wouldn't be some kind of real world situation. So, or it wouldn't actually count. So we'll erase that one for now. And we'll see if we can come up with some other one that's a little better here. So I think if I put in 3, let's try 3 for my number here. Let's say I hit 3 doubles. That might be one that'll also work. 2 times 3 would give me 6. And then subtracting 6 from both sides, just like solving a little equation. 3y equals 12. Divide 12 by 3, I'll get 4. Here's a good combination. And again, what is this combination saying? It's saying that to get 18 total bases, Joe could hit 3 doubles and 4 triples. Again, almost like an ordered pair too. I mean, really, it is like an ordered pair. So that's kind of the form I would like students to put them in, either like a table like this, or they could think of it like an ordered pair in parentheses as well. Same thing. After a student finds a couple ordered pairs, they may start to notice a pattern. In this case, these are the first 2 ordered pairs that would work: 0, 6, 3, 4. So notice I went up by 3 here. So if I do that again, I bet you 6 will work. 6, 2, this will be a combination because I noticed that I went up by 3. So if I go up by 3 again for my x's, and every time that happens, I go down by 2. Down by 2. They'll start to see patterns as they're making combinations. So let's try this one out. Coming back up here to the top and plugging this number in. What if I try 6? 6 doubles, what happens? Well, 2 times 6 would be 12. And then subtract 12 from both sides. 3y equals 6. Divide both sides by 3. Y equals, what do you know, 2. So that does work. That's a combination that would also get me to 18 bases. And I think in this case there's one more. If I just continue the pattern, I keep going up by 3 here for the amount of doubles. I'll get 9 and 0. And so that means I hit 9 doubles, which 2 times 9 would be 18. So that's 18 total bases, and no triples. And I can think that one also makes sense. So again, the combinations, sometimes students have a little trouble with that, but they will start to, as you find one combination, find 2, you can see patterns as you go, kind of like we did here. Every time, if I just keep going up by 3, I get to a new combination, or down by 2 in the other column. So it can be kind of a guess and check thing, but also keep your eyes open for patterns that may help find some combinations for you. One more example to show too, just to go through together to make students realize that sometimes they don't always give us just the straight information. They might not just give us, here's one rate, here's another, and then here's your total. Sometimes we may have to work to find one of those 3 things. In this problem here, they're talking about your class is taking a trip to the public library. You can travel in small and large vans. A small van holds 8 people. A large van holds 12 people. And your class could fill 15 small vans and 2 large vans. What they've given us in this problem, as we'll start to get better at these and realize, but they've given us that, okay, a small van holds 8 people. Okay, that's kind of like a rate, so 8 people for every small van and 12 people for every large van. They've given us A and B here. What we don't know is how many people we could actually take, or how big is our class, what our total amount. We don't know C. But what they have given us is some combination to work with here. They do tell us this though. Well, we know that our class could fill 15 small vans and 2 large vans. And we're kind of assuming that means they would be totally full, no seats left over, and that would be the total amount of kids we'd have. Well, knowing this is like a combination we can use to figure out how many total kids are in the class. If I take 8 people for every small van, and I know we can fill 15 of them, add that to 12 people for every large van, and we can take 2 of those for this combination, that can tell me how many people are in the entire class. So in this case, 15 times 8, that'd be 120, plus 2 times 12, which is 24. So in this case, we're figuring out that we would take, 144 people total. That's how many are in our class. There's our number for C. So now if I'm going to make my equation to help me figure out, that was part A, write my equation in standard form. Here's C. I know my 2 rates now. 8 people for every small van, 12 people for every large van, and we got a seat, 144 people. There's my equation for part A. So now I could figure out some combinations for part C as it is in this case. So just also so students are aware, and we'll look at some problems like this together too. But sometimes they don't always give us all the information, all the A, B, and C. Sometimes we have to find one of them. In this case, they left out the total number we're looking for, C. But if we just use the information they give us, we can figure out C, and then we can figure out some combinations as well.